that watch the recording can hear me. Okay, let's start because we have a lot to go through. First, the obligatory who am I slide. So my name is Johannes Segitz. I'm a SUSE employee, part of the security team there, and I'm based in Nuremberg. I mainly do code review and product pen testing. So before we release a SUSE product, I take a look at it and see if I can break it. For me, it's the first time Nashville. It's a really great city, but I think I have to go on a diet after this week because I ate some bacon with bacon and a side of bacon for breakfast, and that was pretty tasty, but definitely not something I can do all the time. So, what we'll cover today. We will talk about stack canaries, Fortify source, address space layout randomization, no execute memory, stack clash protection, and railroad. Originally, it was planned to do that with a colleague, but unfortunately did not get a visa, so he's not allowed to travel here, so I have to do it all by myself. These are all used by SUSE products. There are other protection mechanisms out there, but these are the ones that we have by default in SUSE. This talk will require some C and assembly background. It's not as bad as it sounds, because since we have those 6 segments, you will be able to follow at least up until a certain point, and then you might space out after a while. But we start again with a new section, and so if you're not that technical, it's not that problematic. I saw that apparently you could submit your talk for technical advanced, but I could not select that option, so I had to choose intermediate. So I hope that's okay for you. So this is just a short overview of what we are doing. Obviously, I mean, 1 hour is not a lot of time. So as a general mechanism, we are talking here about stack-based buffer overflows. And there are different data structures that are used by programs. The stack is one of the main data structures, and we are talking here about countermeasures for stack-based buffer overflows. This is a problem in languages where you manage your own memory. So prime example here is obviously C. In other languages like Python or Java, where the runtime takes care of memory allocations, this is not a problem, because if you have a buffer overflow there, then it's a problem of the runtime itself. You fix it once, everyone's protected once they have the updates out. Unfortunately for C, we have to fix it at every place where this goes wrong. And if you take care, or if you look at CVEs, then it goes wrong a lot. So this is a really simple example here. We just have a main function, we have a statically sized buffer, and then we copy the first argument given to this program into this buffer. We don't have any size check, so as soon as we put more than 20 bytes in there, we run into a problem. So that's the general problem. For a given buffer size, you place too much data in there, and usually you just miss a size check, or you might have a size check, but it might be faulty. So either you can circumvent it somehow. Often you have something like integer overflow, so if you have some calculation in there, then an attacker can do it in a way that he tricks this calculation to overflow. The condition is still fulfilled, you get into the vulnerable code, and then you again have a problem. So why is this a problem? I mean, we could say, well, you overflow a little bit of data, what's the big deal? The big deal is that in our architectures that we use, we mix application data and control information about the execution on this data structure called the stack. So we have a small visualization here. We have 2 functions, function A that then calls into function B. And we have this stack data structure. So currently we have the local variables of function A here. And as soon as we go to function B, we place the parameters for function B onto the stack. And we also place the return address where we want to continue execution once we get back from function B onto the stack. And so we mix those, and as soon as we are able to overwrite this return address, we might be able to get code execution. So as soon as we are able to overwrite it, we have a problem here. And usually the problem is just a crash, but if you do it carefully, then you might be able to execute your own code. This is a small visualization. So if you have NOP instructions, so NOP instructions are instructions that don't do anything. They're usually used for padding or something like that. Then you have the exploit code that you actually want to run, and then you have the return address that points into the NOP instructions. And if you overwrite this buffer and manage to overwrite the return address, then once we jump back to this return address, we jump to our exploit code and we won. So this is not the only overwrites that we have. We can also overwrite other things than just those saved return addresses. So RIP and EIP are the register names. This is the data displays on the stack. We can also overwrite function pointers. So if we have a function pointer on the stack and I'm able to overwrite it, the next time this function pointer is called, I'm in control again and I won. We can overwrite exception handlers. Those exception handlers also have their addresses somewhere on the stack. If I can override that, trigger an exception, then again, I'm in control. Sometimes it's enough to just override application-specific data. So let's say you have a flag that indicates that you're a privileged user, and you are able to write whatever indicates true into this field. Then you might not need to run your own code, but you might be able to just have the privileges that you need. So what can we do against these problems? I mean, the easiest solution would be we just use Java for everything, done, we are safe. Obviously, this does not work. I mean, we should really not use C for stuff that we build now unless it's really necessary, but in some cases it just is necessary. And we also have a huge legacy code base that will not go away. So if you think that there are people that still do Fortran for some banks, then I think we will live with C for the rest of our life. So this is a simple example of 32-bit exploitation. We have a main function. We jump to a function that is called vulnerable. We have the statically sized buffer. Then we read too much data into this buffer, and then we return. So it has no useful functionality apart from the vulnerability. And now I will show you how easy it was to exploit something like that without the mitigations. And as always with demos, let's pray that it actually works. So this is the exploit that we will run soon. We have our shell code here. Looks pretty cryptic. You can either do that yourself or use some tool that generates this shell code for you. In this case, I used MSF Venom. This is a tool that generates shell code for you. This snippet will just add a second root user to the system with a password that is known to us. And then we generate our NOP sled, so these instructions that don't do anything. We have an address where we know this shell code will live, and in the end we just concatenate everything and print it out so that we can give it to our program as an input parameter. So currently we don't have a root 2 user on the system. And now if we go to our debugger and start to run that. So we will see that quite a few times, so I will explain it shortly. Here we have the registers. Those are small variables in the CPU. So this is the data where the CPU can access it really fast. Then here we see the instructions that are currently executed. This is the one where we currently are. Here we have a representation of our stack. And this is just normal GDB with a plugin called PIDA that is pretty helpful for exploit development because it's colorful. So with every key press I do here, we will jump one instruction further. So you see every time we go one further. And now we are at the point where we are at the read instruction that we saw before. So at this place, the buffer overflow will happen. And if you look now at the stack and just memorize roughly how it looks, and we jump over this read instruction, then you will see that quite a bit changed here, and you will also see that we have those 90 hex bytes here. This is the code for these NOP instructions, these instructions that don't do anything. So apparently the shellcode that we want to execute is now on the stack. And now it gets interesting, because if we continue, then we are finally at this red instruction, and this red instruction takes the address on the top of the stack and jumps to this address to continue execution. So with this way, we save our place where we want to continue execution if we go to a different function. But we've overwritten this control information, which we can see here, because We've written this address, and Peter is really helpful. It shows that it points directly into those 90 bytes. So if I step one step further, we are in those knob instructions where we want to be. So we're currently running our own exploit code. If I now just continue, it exits. And if I go to a different terminal, I can now SSH into the system with the password, and I'm here as a root user. I'm here as a root user because the original code runs as root. So it wasn't a local exploit to gain root privileges. This is just my virtual machine where everything runs as root. Don't do that, please. So that's how easy it used to be. Pretty nice for the attackers, pretty annoying for us. And because of that, we have those mitigations, and I will now introduce stack canaries. So the concept is based on those real canaries they had in the coal mines. They were intended to alert miners if deadly gases build up, because those canaries were more sensitive to them. And if they either dropped dead or stopped singing, then the miners knew, okay, we have to go out. And we have something similar for our stack data structure. So the general idea is that the compiler adds so-called canary values at a certain location in the stack frame. And before we return, so before we come to this return instruction, we then check if this canary value is still the value that we expect to be there. And if it's not, then we say, well, something changed our stack, and we bail out. There are three types of canary values. There are so-called terminator canaries. Those consist of a null byte, a carriage return, line feed, and -1. And the reasoning here is that usually you have those buffer overflow problems in string handling functions, and you have a tough time writing those bytes with string handling functions because they usually terminate there. Then there are random canaries. So there you just take a random value. The logic here is that the attacker can't know this random value, so he can't write it. And then we have so-called random XOR canaries. So you take a random value and then you XOR it with certain data on the stack to make it a little bit more unique to the location. We use random canaries. That is good enough because the attacker is not able to know the value. So this is enabled since /10, so already for quite a while. And if you have been to other sessions or have been to SUSECON before, you know we have this thing called a build service. And that is pretty convenient because we just enable it once and then everything just gets this mitigation, which is nice. There are 4 variants in GCC. We have fstack protector that will add this protection code only if you have a buffer equal or larger than 8 bytes in size. After a while, people noticed that fstack protector doesn't catch all the cases. Now there's fstack protector strong. There are some additional criteria. They are pretty technical, but it just takes care that some exploitable cases are now also covered. Then there's fstack protector all, so you just add it to each and every function. That is obviously not great for performance. And then there's fstack protector explicit. So there you can annotate your function and say, well, I just want to have this protection here because this is like the critical entry function or something like that. So, short reminder of the example code here. We have this statically sized buffer. We copy too much data into the buffer. So this is what you see if you compile that as assembly. You don't have to understand all of that. The interesting thing is, as soon as we compile that with fstack protector, it becomes a lot longer. So we have these additional sections. The first one is here. We take the stack canary that is at a predefined memory location, copy it into a register, and in the next instruction, we then copy the content of this register onto our stack. So now we have that stack canary in the stack where we want it to be. And then before we return, we again take the stack canary back from the stack, and then we XOR the stack canary we got from the stack with the known good stack canary. And if you XOR 2 equal values, you get 0. And based on that, we can then test if we have 0, we go to the normal leave and return instructions. But if we don't have 0, then we know something changed here. And then we call this stack check fail function. So then we can bail out. So I will now demonstrate that quickly. So we have a binary compiled with stack canaries. It's the example you just saw. So if we give it 12 A characters, we expect that nothing happens because it fits into the buffer. If we give it 32 A's, then it terminates because it detected this stack smashing. And we now see that again in the assembler. So we are here in the beginning. We now take this value from the memory where we know that the stack canary is stored and move it into RIX. And unfortunately, it's not visible here, but if we jump up a little bit, you see now this is our stack canary, so it's rather long. And if we, with the next instruction, we store it on the stack, and if we now continue, we are now at the place where we get the stack canary back from the stack. So we had the overflow already. We move it into RCX, sorry. So here we have RCX. And if you noticed, we now have this ending in 41, which is the hex representation of a capital A. So since we fed it with a lot of capital A's, we probably overwrote some of that. And with the next instruction, we will XOR them together. And if we now look into RCX, this should now be 0, because we should have the same values XOR together. It should be 0, but it is not 0 because we overrode it. So the jump will not be taken, so we will not go to the normal return instructions. And if we now continue, then we see this warning that we saw before. So execution is stopped before something bad can happen. So now we get to the interactive part. People usually loved it. So every mitigation has its limitations. Can you think of some limitations why this might be problematic?
That's one thing I was wondering is you could look at, can you examine the source code of the actual fstack protector and then modify the stack in such a way that you emulate those canaries or something that you could?
You would need to know the random value, and this is generated every time you launch this code. It gets a new random value, so I think it's tricky. I mean, I have some bullet points about that on certain systems. Any other ideas? Okay, perfect. More time for questions later on. First of all, it does not protect data before the canary. So let's say if some function pointers there, you might be able to overwrite those function pointers. And since you don't overwrite the return address, which is after the stack canary, you might not notice that. Some implementations are smart enough to reorder variable layout on the stack so that they place stuff like function pointers behind the canary so that they are also protected, but that's not a given. And also, let's say you have this administrator flag, you might be able to override that and it might not be noticed. It also does not protect against generic write primitives. So sometimes as an attacker you have great luck and you can say, well, write me this value to this location. And then I just override what I need to override and skip the stack canary and then I'm good again. You can circumvent that with exception handlers. So if I override the address of an exception handler and trigger the exception before I get to this checking code, then again, I'm in control because this checking code is then not executed. You can always just chain the buffer overflow with an information leak. So if you manage to leak information from the stack and you manage to leak this random value, then you can write it. And you have no protection for inline functions because this all depends on this function prolog and function epilogue where you go to the function and then jump back. But if you inline the code, then there's no function where you can have this checking code.
You said the information leak there, the random value for the stack canary is generated every time you execute the function, or when you compile it?
It's generated every time you invoke the process.
And if it was leaked, how would it help you? Because it would be changed the next time you ran it.
Yes, but so for the lifetime of the process, it's still static. So let's say you have web server running, I leak the information, and then maybe I can attack right away, or maybe I can just do it with the next. Yeah. It can still be used to cause denial of service, which obviously is better than having someone run code on your system, but still pretty bad. Yeah. So, I mean, as you've seen, this is definitely a really helpful mitigation, but still there are quite a few drawbacks. So it's not like a magic bullet that will protect you in any case. So let's jump to the next mitigation, in this case, Fortify source. This transparently fixes so-called insecure functions to prevent against buffer overflows, and those insecure functions are functions like memcopy or something like that. I set insecure in italics because then you have situations like these. You tell people don't use string copy, use the way more secure string L copy, and then people just use it incorrectly. So you can use string copy securely, you just have to check what you're doing there. What is checked there is for statically sized buffer, the compiler can check or add checks to certain functions. So if the compiler sees, well, this buffer has space for 20 bytes, then I will add a check there that only 20 bytes are copied into this buffer. You enable it with d45 equals 2, d45 source equals 2, and you only can enable that if you also enable optimization, because this is part of the optimization run. So if you add this flag but don't enable optimization, you will not get the effect. That is something which you need to be aware. And that is also enabled by default since less 10. We have a slightly different example here, because since we need to enable optimization with the original example, it would not work because the compiler would see, well, you don't do anything in this function, so let's just skip it. So we have that little thing here to force it to really actually go there. But apart from that, it's pretty similar. We have a statically sized buffer. We then copy data into this buffer without any check. So we would have the same problem there. This example is based on Matthias' work. This is a coworker of mine. He does regular training for our trainees with regard to buffer overflows and security. So this is part of his work. So this is the code of the original function without any protection. You see the call to string copy in here, so everything just looks like you would expect it. And now if we enable Fortify source, the first thing you might notice, it became a lot shorter. The reason is that we enable optimization. So the code emitted by GCC is usually really, really inefficient as long as you don't enable optimization. But it makes it a lot easier to read because you have a pretty clear correspondence between what you wrote in C and what you get as assembly. As soon as you enable optimization, it becomes faster and shorter, but also harder to read. But the interesting thing here is that we don't have a call to string copy anymore. We have a call to string copy check here. And also we see that the compiler apparently noticed that this buffer was hex 100 bytes sized. So it moves this to EDX, and then this function can check if we actually want to move too much data in this buffer. Yeah, so these two are the important lines here. So I will show that again. So we are in Peter again. If we run the code and enter 100 A's as input, then we should actually see something. Okay, perfect. So you see pretty much the same listing. We just continue to step over that, and now we are at the check function, and if we step over this function call, nothing happens, everything is what we expect it to be, and if we continue, it will just exit normally. If we run that again and enter 700 A's, then this will not fit into a buffer. Now we are at the same place. We start to step here, and if we try to step over this string copy check invocation, then we will not be able to step over, but we will be in this different code path where the code noticed that something went wrong. You wanted to place too much data into this, and there you then just bail out. So really easy, and the nice thing is you don't have to do anything for it. So, again, any limitations you can think of? Any problems?
Detecting the code patterns could be hard.
Yes. So, I mean, this was a really simple example that it's really easy to see the problem. But if you become more complicated, then the compiler might not understand that anymore.
Seems like if the calling code properly checked the buffer before it called the subfunction, if you check twice, it would be a little bit performance hit.
Yeah. I actually don't have that as my bullet point, so I have to add that. That's a good thing.
Is it only for particular functions?
Yes, also.
So as some new exploit comes out, you could use the exploit that it's not.
Mm-hmm. Okay, we covered quite a lot already, so it's limited to certain functions. You don't have the protection for everything. It can still lead to denial of service, same thing as before. It just kills the program. Developers might keep using these functions. So if you tell them, well, it adds those nifty checks for you, then they might think, well, great, I don't have to write them myself anymore. The compiler will do it. But it comes with almost no cost. So it might not be perfect, but since it comes with almost no cost, and the small performance hit that you take there is just for the check that you should have already. I mean, that you don't have the check there is not a performance optimization, it's just a security problem. So in my view, this is not a performance hit that you take there, it just adds the code that you should have wrote in the first place. So let's go to the third mitigation, no execute memory. In modern processors, and modern is pretty interesting term because everything that is not totally ancient, they support memory to be mapped in a way that it's non-executable. So another term for that is NX or this, which I can't pronounce, but if you read it, then it's the same. The most interesting memory region for that is the stack and the heap, because usually you don't want to execute memory that is on the heap. So that usually does not make sense unless you build a JavaScript interpreter or something like that. But for normal code, you usually don't want to do that. So the buffer overflow might still take place, and the attacker might be able to overwrite these data structures, but he can't jump to this code because the code can't be executed because the whole memory region is marked as non-executable. So if you look at this file in the proc file system, then you have the memory mappings there. And if you just grab for stack here, then you see, okay, our stack is at this location, and there you have certain privileges here, and you can read it, you can write it, but you can't execute it because you should have an X here if you want to execute it. So in this case, your stack is not executable, you can't jump directly there. So, any ideas why this might be limited in some way? So the first thing you can do is you can just use existing code in the program. I maybe don't have to jump to my code. Maybe there is a privileged administrative function I want to use, so I just jump there. Since it's in your code, it must be executable. And again, this might be something that I can exploit. You can do something called return to libc. Pretty much every non-trivial program will have a large amount of libraries linked into this process. So if I can jump to the libc functions to execute something, for example, then I can use the existing code there. I can use something called return-oriented programming. Return-oriented programming is pretty nice because there you look at the memory regions, and if you have those return instructions I showed you before and a few instructions before that, then I can structure my heap, my stack in a way where I go from small instruction to next small instruction, and I never execute code, but I only use my stack to control where I'm jumping next. It's a little bit complicated. In my other version of the talk, I have some slides to show you exactly what it does here. But in the end, you can then build from the existing code base almost any functionality that you need. So it is assumed that every non-trivial program contains enough of those so-called gadgets to build whichever behavior you want. So the next thing we are going to talk about is stack clash mitigation. This is something rather new. If we look at this maps again and look at the heap and stack region, then you see that the heap is at this address and the stack is at this address. And what would happen if those two met? So if those two grow together so that they will then clash or meet. To prevent that, we enter a so-called guard page between those two, so that if something like that would happen, then we would notice it, because then you get a segmentation fault. Unfortunately, sometimes you can skip the guard page. So if you bring the stack and the heap really close together, so that you only have the guard page between those, and then use an allocation larger than one page, you might be able to jump over the guard page without the guard page being touched. And then you are able to have stack operations that then write into the heap memory region or the other way around. And that is obviously a big problem, because that is not expected by our programs, that if you write to the stack that the heap changes. To prevent that, you can compile your code with fstack clash protection, and that causes the compiler to then enter code that will prevent this problem. It ensures that for every page size allocation, or for every allocation, you will get access to each page at least once, so that if the guard page is in there, it will be triggered. So we have a somewhat contrived example here. We have a function called fancy print that takes two arguments. So then we use allocate to allocate a space on the stack, copy those two strings together. And since those two strings come from our command line arguments, we are able to control them. And since there are no limitations, we can make those arguments as big as we like. And if we make them bigger than 4K, at least on this architecture, then we have an allocation that is larger than page size, and we might be able to jump over the guard page. So I will only show you part of the assembly here. So this is the second string lang command we saw in the example before. Then we have quite a few calculations here. That is again because there is no optimization. What it basically does is just calculates how much data we want to then subtract from the stack pointer. So you could say this is basically one instruction to say, well, how much data do we actually want to remove? And then the next instruction, we then just take the stack pointer and subtract what we calculated before. If this is smaller than 4K, this is not a problem, because we would again hit the guard page if we then accessed the stack. But if this is larger than 4K at this point, then we might skip the guard page and not notice it. So if we compile that again with this compiler option that I showed you before, then again we have this calculation, which is pretty inefficient because there is no optimization. And then the next part is a lot longer, so we don't just subtract it, but what we do here is we loop over this whole construct, and with each loop we do here, we subtract hex 1000 from the stack pointer, so the size of a page, and then we touch the memory at least once. We don't change it, but we have this access, so if we have the guard page, this will trigger the guard page, and then again we at least notice that something went wrong here. So, any ideas what the limitations of the stack clash protection could be?
It would just be a DOS, right?
Yeah. So this is like the default limitation of all of those mitigations. One of the main problems here is it only works for calculated allocations. So, for example, if you have a giant struct and you place this struct onto the stack, then there is no calculation there, so the compiler can't add this code there. Some edge cases are also not covered, so let's say you have some inline assembly. Then in this case, you also will not have this mitigations because the compiler doesn't touch that. You have a minor performance loss, of course, because it's much easier to just have this one instruction where you subtract from the stack pointer. If you loop over this and touch every page, that obviously is slower. But in the end, you get what is guaranteed by the architecture itself, and usually you should not have gigantic stack allocations. So if you have that in your code, then something is a little bit fishy usually. So in my mind, this is definitely a high-value mitigations with almost no downsides. I don't know if you remember, but we had one of those code name security vulnerabilities some months ago called system down. So there was a problem in systemd in the journal component, and there they managed to have this stack clash. And luckily, we were not vulnerable, at least on many systems, because this is enabled since /15 by default. So all of /15 is compiled with this option. And all /12 updates that go out also have that. But since this was not available when /12 was initially created, not all of /12 is protected, because I think a lot of customers would not be happy if we would re-release the whole of /12 as an update. That would probably not be appropriate. So, next protection, and then we go back and check if my other slides have ASLR. This is RELRO. That stands for relocation read only. So the first question is, what are relocations? Relocations are a level of indirection that allow code to run at arbitrary location. Now it would be great if we talked about ASLR before, because that references that a little bit. On modern systems, if you run code, it will not run in the same memory location every time. It's usually shifted to a different location every time you run it. That is also a good mitigation, because then you can't use static addresses to jump to your code. And also, if you compile your binaries with fpy or fpic, or if you use dynamic libraries, this is in general necessary. So since you can't know when you call, for example, printf, where printf will be at the time of invocation, you need to fix up your printf invocations at the time that you load your code, since you can't say, well, it will be at address foobar. So we have a small example code. It's really simple this time. We basically just call printf twice. And for the first printf, we don't know where it actually is. So a component called the dynamic loader first needs to find out where printf is in this case. Then it will save the address to a certain data structure. And the next time we go to printf, this will already be resolved, so we know where printf is, so we don't have to go through all the hassle again, but we can jump directly there. So, yeah, well, what I just said. And now I will show you that quickly. So, basically just that short example. We have puts here instead of printf. That is just because the compiler decided it's easier for him to use puts. And if we now start to run this, we are here at the beginning and we continue to step over that. And now we're at the point where we call this function for the first time. And if we don't step over that, but step into this code, then we are here at this place where it will try to jump to a certain location, and this is the place where you have this relocation. And since we call it for the first time, it doesn't know where it actually is. So it will take the jump, but it will jump directly to the next instruction and then just continue there. So the interesting thing here is that we don't jump to the printf function itself. If we continue now, should have said a breakpoint. Let me. So I just step over that. You already saw that it will not jump directly to the code, but into this relocation thingy. And for the next printf, if we now step into that, then you see that it will not fall through to this point where it goes to the relocation, but it will directly jump into this printf or puts function. So now it already stored the address where it knows this function to be. So the problem here is that if I'm an attacker and I know where these relocation information is stored, I can override it. So I can override the address to my shellcode there, and the next time you call printf, you don't call printf, but you jump to my exploit code, which is obviously not very great. And against that, we currently have something called partial rel row, and that protects you against buffer overflows and global variables, and this is enabled since less 10. And currently we are testing full rel row in factory, and full rel row will then ensure that those entries are not writable anymore. So even if you have other overflows, you will not be able to exploit that. But this is a little bit tricky. We currently have quite a few build failures because apparently some code is assuming that you don't do that. So this is going to take a while until we have that for all many thousand packages that we have. We have a drawback of full rel row. So that only works when you start a program, you need to do those relocations. So we can't remove the need for the relocations. There's no way to remove them completely. What we can do is we start a program, then we do all the relocations, and then we make this segment read-only so that you can't write there anymore. But that requires us to do all the relocations when we start the program. If you launch a huge program, let's say LibreOffice, then that definitely adds to your startup time. Because let's say you start LibreOffice and you just want to write one sentence and not use all of the functionality that LibreOffice has, we still have to do all the relocations for all of LibreOffice. So the larger the code base, the more relocations you have, and the less of the code base you actually use, the worse it is actually for you. If you have a code base that is rather small and you use almost all of it, then it's not really a major drawback, because the performance hit that you take at a startup is something that you then later on don't have as a performance hit anymore. So let's look if my other slides are now here from Nuremberg. Okay, then I will do it without some attack. That would be great. I just say it was my colleague that's not here. Then I will just explain to you without slides. So as I outlined earlier, ASLR ensures that if you run a program, that it's not loaded on the same address every time. So computers are deterministic most of the time, unless we do something against that. So if you run a program and you run it again, then without any extra effort, it would just run at the same location. And if you remember the earlier example that we had before, I knew exactly where my shellcode will reside, so I could hard code the address of my shellcode in my exploit. I could say, well, for this given version of OpenSUSE Leap, the shellcode will reside in this address. But if we move around the program every time we invoke it, then I can't hard code this anymore. And this is really a huge, huge benefit. So I can tell you, if you write an exploit, it's really, really annoying if you have to deal with ASLR, because either you have to find an information leak where you can get this information before, so you can calculate where all things are going to be. So you need a second vulnerability that you have to use, and your exploit becomes a lot more complex. Or you get lucky and find some information in a register, for example, that you can use. Or you get lucky and have a limited architecture like a 32-bit architecture. Because in a 32-bit architecture, you have a 4 gig sized address space, and in this case, there's not much room you can move around. Because 4 gigs are not that much today anymore. And since you have your stack, your heap, and everything in this address space, there's just so much entropy you have there. So you might be able to brute force it. But on a 64-bit architecture, there's usually no way to just guess where you have to jump. So that makes the life of an exploit writer a lot harder. On pretty much every modern system, you will have ASLR enabled. You can check it in your proc file system. And if you don't have ASLR, I mean, you are a SUSE customer, so you have it, but let's say you have other systems that are not SUSE, which I don't approve, but it might happen, then you should check if you have ASLR there, because that is really an important mitigation. It has almost no drawbacks. You used to have some performance drawback on old hardware, but on 64-bit machines there is almost no performance hit. You should have it enabled all the time. This is really, really important, because exploitation is just really easy without it. Yeah, so sorry that I don't have the slides there. I don't know where they went. So, as an outlook, exploitation definitely got a lot harder. You've seen that with the example. The original exploit was really, really short. If I write an exploit against all those mitigations, it's a lot longer, it's a lot more fragile, it might not work all the time. You usually need more than one vulnerability, and that's the reason why those vulnerabilities are now pretty expensive. So if you have an exploit that works against the modern Chrome version or something like that, then you can earn like $1 million for that. So the days where people just shared their exploits for free are definitely over, because nowadays it's a huge effort to exploit something like that, and that's to no small part thanks to the mitigations there. ROP, this return-oriented programming, is used in a lot of modern exploits, because with ROP you can circumvent this no executable memory. And since this is also default nowadays, you will find ROP in almost every exploit. There are several countermeasures against that. You can have so-called shadow stacks. So we've seen that the problems with buffer overflows is that you have this control information intermixed with the application data. And a shadow stack is just a second data structure where we just have the control information. So every time we jump to a function, we write the return address to the normal stack and to the shadow stack. And before we return, we check if the information on the shadow stack is the same as on the normal stack. And if they are not the same, then we obviously have a problem here. Then there's something called control flow information. So there you ensure that only the jumps that the programmer actually intended are taken. If you look at the exploit code, we jumped to a certain place and the programmer never had instructions to jump there. So with control flow integrity, there are several techniques to ensure that those jumps are not allowed. More and more you get hardware support for that, because unfortunately those mitigations are rather costly. So the other mitigations I showed to you, they either have almost no performance impact, or it's a performance impact that people nowadays are willing to take to have more secure software. But for CFI, so for this control flow integrity and shadow stacks and something like that, you can easily have performance impact of 5 to 10%. And that is usually not something people are willing to take. So keep your systems updated, because with all of those mitigations that I just showed you, it's still possible to exploit security vulnerabilities. Otherwise, we would be in a completely different world. But as you've noticed, it's still possible to exploit that stuff. But luckily, it's rather seldom that you have this nifty zero-day attack where a great nation-state attacker attacks your systems. Usually it's really the low-hanging fruits. It's the never-patched system that is 5 years old, connected to the internet, and there's a vulnerability that doesn't even require me to exploit anything. It's just an administrative console, and I can upload my own script and launch it. So that is way more often the case than some nifty combination that circumvents all those mitigations. So with that, thank you for your attention. I'm sorry that the ASLR part is not there. You can have the slides here, but unfortunately they are the incorrect slides. I will upload the correct slides later on, or you can just scan this QR code and you should get the slides now. So if you save then the URL, I will, right after the talk, check why we had this problem. So thanks again, and any questions?
Any of these, I know, the techniques with the canary stuff, is that used in the compiler, used for the kernel, or as well? Because, I mean, there's a different kind of thing. You're already the kernel, so, but you want to protect against
Yes, so stack canaries are used in the kernel. You can configure that. I'm currently in contact with our kernel guys to improve the mitigations that are in the kernel. But that is a rather sensitive topic there, because in the kernel, if you have a performance slowdown of 1 or 2%, there are quite a few customers that will not accept that. So my idea would be that going forward, we could maybe have a different kernel flavor, because already now we have different kernel flavors for different needs. We might have a kernel flavor that has more of those mitigations, where you say, okay, this is a really critical system for me. I just buy another server. I don't care if it gets a lot slower. I can mitigate that. But this is an ongoing discussion. But in the kernel, it's always a lot harder, because performance loss is a lot less accepted. And also those mitigations in user space, they are usually rather easy, as you saw. And kernel space is a different beast. Any other questions? Okay. Thank you for your attention. I'm always available for any other questions, and I will update these slides here as soon as I figured out where my ASLR part went. Thanks.